Howdy, everyone. Happy Wednesday. I apologize for missing class on Monday. As it turns out, about 2 weeks ago, I twisted my ankle and I thought it was going all right. Unfortunately, just a few days after I twisted my own ankle, my wife also twisted her ankle. So we both wound up going to the doctor on Monday, hoping to get just some guidance. But he had us take x-rays, and turns out we both have cracked, I guess they're fibulas, the small bone in the leg. So we both are now wearing boots. I appreciate the many nice notes I got from you wishing me well. And luckily we have Zoom. So if we were doing regular classes on campus, I would not be able to do them, but I'll be able to do Zooms. I should also mention that we will not have a live class this Friday. Tomorrow and Friday, I have to serve by Zoom on a National Science Foundation panel. And so I'll be tied up all day on Friday with that. So that means you have missed 2 lectures. And what I will do as soon as I can, probably on Saturday, I will record 2 lectures that you can look at your convenience, but hopefully you can look at those before we get back on the regular schedule next Monday. On the slide here, I'm showing you a cartoon referring to Bunsen. And just out of curiosity, everyone please send me a chat answer whether you've used a Bunsen burner or not, and whether you used it in high school, freshman chemistry, or both. And so I'm just curious, back in my day, we all did that. Okay, well, it seems like everybody has used it. So at least his name went down in fame, or at least he's famous for having his name in the little Bunsen burner. Based on what I've been telling you, remember we talked about doing the Bunsen burner flame experiment? That's the kind of stuff Bunsen was doing. He would throw barium salt into a Bunsen flame and he would see green colors, and he would realize that there were certain frequencies of light and therefore certain energy transitions that were coming out. So that was sort of the beginning of understanding atomic spectroscopy. Obviously, you can't do that with hydrogen because you just burn the silly thing up. But with salts and some metals, you can do these flame experiments. Okay, so remind you where we are. We are talking about the hydrogen atom. And we completed talking about the Bohr model of the atom. And the beauty of the Bohr model was it gave us the exact correct energies. So I don't think I've written this into your lecture notes enough, but just emphasize for yourself that the energy of an energy level for a hydrogen atom is minus R sub h over n squared. And so if you want to know the energy level between any two states, you just figure out what those energies are, and that's going to be the transition that you have. So let's say we want to look in this diagram, this N2 to N1 transition. Energy of the N1 is minus 109, the 1,000. That's the Rydberg constant divided by 1 squared. It's still minus 109,000 wave numbers. When you go to the next level, it's the Rydberg constant divided by 4, or n squared, where n is equal to 2. And so you wind up with 1/4 of the stabilization in an N2 level that you do in the N1 level. So if you want to know the energy difference between these, you just take the difference. Now, a lot of people start asking, well, when you do this equation, which one is N1 and which one is N2? And my attitude is, it doesn't matter, I don't care. Just remember to take the difference between two energy states. If it's absorption, then you have to put in energy of that magnitude. If it's emission, then it's coming out. So in this diagram, this would be an emission, and you would get about 82,000 wave numbers frequency or wave number coming out of the system. If it's absorption, you have to put in delta E equal to h nu of 82,000 wave numbers to get from here to there. Okay, so that was the Schrodinger, sorry, that was the Bohr model. And I think we got started a little bit on talking about what Schrodinger did. But basically, he went off into his winter resort cabin and played around with the information that he knew what the energy levels were. He knew with the de Broglie relationship. And there had already been demonstrations that particles had to have wave properties. So I'm going to go quickly over the second page, but the first page here is quite important. In the final solution for the hydrogen atom, which is exact according to the Schrodinger equation, it can be split into two parts. And when you get done, you wind up with three constants that wind up typically having to be integers. There are three quantum numbers. So we can treat this as a single particle for the electron and treat it in 3 dimensions in spherical coordinates, r, theta, and phi. And our quantum numbers are going to be n for the principal quantum number, L, that's the one that's going to tell us if we have sp or d orbitals. L equals 2 means a d orbital. And m sub l's are the components of L. So as I've written here, so if L is 2, they can go from +2 down to -1. The important part is Schrodinger found that he could split the overall wave equation into two parts. This is called the radial part. Capital R is a radial function. It depends only on little r, the distance the electron is from the nucleus. And we're going to find solutions for this will depend on the principal quantum number n and the angular momentum quantum number L. The second part is an angular part with theta and phi, and we call it capital Y. It depends on the quantum numbers L and m sub L. Capital R is going to give us the energies of the state. Capital Y, as we'll see today, will give us what the orbitals look like. Okay, so just to start, here's some solutions for the hydrogenic radial wave functions. Hopefully you remember from last time that I told you this can be applied to He plus or lithium +2. Just so you have one electron around a nucleus, the nucleus could have a +1 charge, +2 charge, +3 charge. So that's why the Z is in there. To make the table simpler, you'll notice the exponential terms each have a -1/2 rho. Rho is defined as 2zr over Na0. So the n refers to the 1 here for the 1s orbital, or the 3 that we have the 3s orbital. Z for hydrogen is going to be 1. So the very first exponential term will be e to the -1/2 times 2 R over A naught. So the 1/2 and 2 cancel out, and it's just e to the minus R over A naught. All the junk in front is just a normalization constant that we have. And then all of these others can be figured out. And as you might expect by now, people can go up to 6G orbitals and write these things out exactly. These are exact solutions that you can get for the Schrodinger equation. But as you can see, the solutions aren't particularly simple. So these are the radial functions from which the energy levels come from. Okay, so here's just a reminder of these are all hydrogenic. They can all be treated by the same model. We just have to put in the Z value for the atomic number. 1 for hydrogen, 2 for helium, 3 for lithium. And I think in assigned problems, which are due a week from this Friday, you probably have to do a problem related to lithium plus 2. And here I'm just parenthetically mentioning the relationship between the helium and the hydrogen Rydberg constant is Z squared, and same for lithium. So 2 squared or 4 for helium, 3 squared or 9 for lithium. Okay, so this is the way it looks, and I'm going to go over this fairly quickly, but I encourage all of you to go home and look at the calculus that's involved here and see that you would be able to do all of this if you had Schrodinger looking over your shoulder and telling you what to do. But you've already learned the basic tools from your calculus course. Okay, so this is our standard equation for the Schrodinger equation. Del squared in spherical coordinates looks like this. Now you'll notice there's a slight change. We have a mu in the denominator here instead of the mass. Before, when we were doing the single particle, we would just have the m in the denominator. Here we actually have 2 particles, the nucleus and then the electron around it. And when the electron spins around the nucleus, the center of gravity changes a little bit. So if the electron is on this side, the center of gravity is ever so slightly away from the nucleus towards the electron. If I remember correctly, the proton is 1,832 times heavier than an electron. So for practical purposes, you have one giant mass in a fixed position, but we can avoid introducing any translational motion into the Schrodinger equation by putting a mu here. We're going to see this mu a lot later when we start talking about molecular vibrations of diatomic molecules. But notice it is the product of the masses, so in this case, the electron and the proton, divided by the sum of the masses. Okay, people are asking about homeworks. There is a homework due this Friday, but it is still on quantum mechanics. So that is still due this Friday. We have covered everything on quantum mechanics. The atomic structure stuff we will finish by a week from Friday, and those will be due a week from Friday. So nothing is delayed on the problem sets. Okay, so what we always have to do with Schrodinger is we have to put in the potential function. And sadly, most of the time, we can't get an exact solution. We resort to computers, we write to special programs, and we can get answers. Luckily for hydrogen, we can do it. So here's the potential function that we put in for the electron being attracted by the nucleus. So the charge on the nucleus will be plus ZE. The charge on the electron will be minus E. E being the charge of a single electron. Now, if you look in your text, this is what the text will show you. And I and most people who work with spectroscopy or molecular structure don't like this. The book uses it because in the 1970s, a bunch of old men and a few women got together and they decided everything needed to be in kilogram meter second units. And so this is supposed to come out as an energy in joules. So in order to get it into joules from the normal stuff you would put in for charges, they put in this conversion factor 4 pi epsilon naught. This is called vacuum permittivity. And it's just a mess because sometimes you have to square it and then you get 16 pi squared, E naught squared around in your equations and so on. So it's just unpleasant to work with. Okay, so we're going to work in atomic units, which basically says we're going to throw out the 4 pi epsilon naught. I'll later show you what the conversion factors are, but this is then what the equation comes down to. And for our purposes, since we're going to do the hydrogen atom, Z is 1, looks very simple, minus E squared over R. So I think I mentioned this last week. The potential energy is just the product of the charges. Proton has charge plus E, electron has a charge minus C, and you divide by the distance between them. So this is what Bohr used, and it worked out just fine. Okay, so we start with this expression, and notice that I've taken all this angular part and I've written this as a capital lambda squared. So I'm using this as an operator. Basically, I'm following what Atkins used to put in as an appendix in his textbook. And I'm quite sure he hasn't put it back in the latest one, but at some point he decided to take it out. But I think it's worthwhile seeing that you could do the math if you had to. Okay, so we're first going to write the separation. This is what is very important that you remember, that you have the two components. So I plug this back into this expression. Capital R depends only on little r, capital Y only on the angles. And so I'm able to write a part here, taking Y to be constant. And in the second part, I take R to be constant, and then I have that operator acting on it. If you think about your calculus and fiddle around with it, you can show that this is equal to that. Next step is we divide through by psi, which means that the Y here would cancel out and we get an R in the denominator. And then for this term, which we're moving to the right-hand side, we get rid of the R and we get a Y in the denominator. So this is the important point of the derivation. Schrodinger saw that he could totally separate the radial part from the angular parts. And this gives us an interesting situation, which you might never have thought of. But everything on the left-hand side of this equation only depends on R. The right side depends on the two angles. And the angles are totally independent from R. And so the only way that these two can be equal to each other is if they're both equal to the same constant. Okay? So that was a key element in there. So that's basically what I've written down here. Turns out this right side of the expression, if you've gone through your differential equations course, is not all that bad to solve. If you put in constraints and stuff, you basically find out that the constant that this is equal to looks like this. So this is the solution for this expression. Once you get the angular part solved, the spherical harmonics as it's called, then you can set the radial part equal to that, and that's this. Schrodinger makes some more manipulations. He comes up with a new function. So this is, again, an operator. And he decides to call it capital pi, not 3.14, etc., but it's a function, and it's little r times r. When I was writing my equations, I should have put a 1 over the capital pi here, so please stick that into your notes. Anyway, look at the rest of it. This is what it comes out to be. And I've given you what the solutions are for the different radial functions. So you could find out one of your solutions, capital R, multiply it by little r. That's what your pi is going to be. Then you solve the rest of it, and that's your equation. Well, when you're done with this, then this is the result that you get. Your book would give you this, and you can see the vacuum permittivity gets to be a holy mess. We now have 32 pi squared epsilon naught squared. In atomic units, it looks a lot nicer. We can further get rid of the z squared if we realize we've got hydrogen with z equal to 1. And then we combine terms here. And notice this is basically what I'm telling you. The energy levels are for each hydrogen energy level. Now there's an HC in here because I'm keeping this all in joules. So when we work in wave numbers, as I was encouraging you to do with the Rydberg constant at 109,000 wave numbers, or centimeters to the minus 1, if you multiply it by HC, you will simply get the energy coming out in joules. And here's my example of what R10 would be. 1 refers to the fact quantum number n is 0 and n is equal to 1, L is 0. So this is the 1s orbital that you would have for any of these systems, and then z equal to 1 if you're doing hydrogen. Okay, so I'm obviously not going to quiz you on any of that, except for the part you need to be sure that you understand we could split the wave function into these two components, and we may have to work on that. The answer, there's a question. Is the Rydberg constant only valid for hydrogen-like systems? The exact answer is yes, but there are many cases where you can find alternative Rydberg constants that have been modified and not solved exactly. I have a good colleague who wrote a chapter into one of my books doing studies of Rydberg spectroscopy of molecules. And what this fellow does, he's in Zurich, Switzerland. What this fellow does is he looks at transitions between quantum states like N45 and N49. So he's looking at inner shell electrons of atoms. So he might be looking at something like cadmium, which will have a Z of, I'm not sure what, 45. And then he'll get really up into those N levels, and he'll look to occupied things there. But strictly for your purposes, for exams, problems, we can only apply it to those three systems. Okay. So this is what we said with the Bohr system, or this one, you get this comes out in joules. And this is where I want to show you the conversion to wave numbers. So energy in joules divided by HC gets us here, and this will now be in centimeters to the minus 1 when you do this conversion. So to show you how that works, notice that when I write a bar over like nu, this is the wave number. That's equal to the frequency over the speed of light, and that's also equal to 1 over the wavelength. And that's the way we wrote the Rydberg equation in the first place, as delta E in wave numbers coming out looking like this. So you can see if I take a difference between two n values, we immediately get what the Ritz equation is there. Now, let's look at how the conversions work. So here is using the way I have this expressed here. So this is in atomic units, basically. So we're going to have mass, generally grams work out the best. Electronic charge, it's called an electrostatic unit in these CGS, gram centimeter second units. And that's equal, in a very strange way, to the square root of erg centimeters. Now, you may or may not have seen this in your courses. It's not terribly important whether you have or not, because we can just go to a table and look at a conversion from wave number to joules or whatever we want. And here we could write H in erg seconds. So if you work this all out, you'll see it comes out gram centimeters squared per second squared, which is an energy unit, and this is an erg. An erg is a small joule. I always forget whether it's 10 to the 5th ergs or 10 to the 7th ergs per joule, but it's a lot smaller. Well, I guess we can figure it out. A centimeter is 100 times smaller, so that's 10 to the 4th, grams 10 to the 3rd. So it's 10 to the 7th times smaller than a joule. Okay, so this is what you would get when you use what Bohr had or what I like to use. The strange part is, what is an ESU? It comes out to be in these units. The way that your book would have you do it, they would throw in this 4 pi epsilon naught squared. And when you throw it in, you have to realize that the 4 pi epsilon naught is in units of joules to the -1. This is coulombs, by the way. Coulombs squared, meters to the -1, and the whole business squared. And then you multiply it by joule squared, second squared, things cancel out, and you wind up with getting a joule. So my advice to all of you is think in wave numbers, think in centimeters to the -1. It's an energy unit. You can look up conversions. 350 wave numbers is 1 kilocalorie per mole. 83 wave numbers is 1 kilojoule per mole. And that's basically the way to use it. But let's stick to wave numbers. And then we'll always say energies minus R sub h over n squared. R sub h is 109,677 wave numbers. Okay. So hopefully that gives you some good feeling for what to expect for the energy levels and units and all that for the hydrogen atom or the helium plus lithium plus 2 atoms. So next, let's look to see where the orbitals look like. And orbitals, of course, the way they're drawn, they are probability distributions. So whether in high school or freshman chemistry, you drew an orbital, you probably weren't explained why they looked the way they did. And they kind of looked like a balloon for a 1s orbital, and you just felt an electron could be contained in there. You were no doubt told the caveat, well, that balloon doesn't contain all of the probability. It can also get outside that. But for our purposes, we now know that we can write wave functions, and we know wave functions can be written in terms of probabilities when we square them. So psi squared, or psi star psi, whichever we need, can give us a probability distribution in terms of the angles. So notice we're leaving the R part out of it. We're not deciding how far away the electron is when we solve for the shape of an orbital. We just want to see what the angular part will tell us. Okay, so let's start easy. We'll first look at the very lowest energy orbital. That's the 1s orbital on the hydrogen atom. And all of you remember this a billion times from freshman chemistry, but it doesn't hurt to remind you. L equal 1 means p orbitals, L equal 2d, L3, f, L4, g, and so on. So when n is 1, L can only be 0, and so there's only one orbital. We put 2 electrons in it. There's only one m sub L. That determines the fact we have one orbital. And the entire solution, both the radial and angular parts, looks like this, because there is no angular part for a 1s orbital as such. So there is no dependence on theta and phi, and so we know the orbital is going to be spherical. So not a very difficult conclusion to come up with. A naught, I'll point it out, is 0.53 angstroms. If you like picometers, it's 53 picometers. This is the Bohr radius. So that's part of this overall solution. So here's my smeared up picture of the 1s orbital that you have. If I take psi squared, this is what the function will look like. It looks like the electron wants to sit as close to the nucleus as much as possible, and then it tails off exponentially, and you've got to get to pretty far A naught values like 9 or 12 I mean, that's still a very small number before this fades out. But theoretically, you have to go all the way out to infinity for the probability to die out. I used to mention in my class that all of these probabilities die out only at infinity. So if you're sitting next to someone in class, for example, there's some probability that electron will get from your neighbor to you. But I think I also mentioned that I had this 14-year-old bright kid in my class a year and a half ago. And he came up to me and said, well, you know, that's not correct because a human body does not have enough electrons to fulfill that probability. In other words, the probability of an electron would have required something like 10 to the 84th electrons from your body going to the neighbor to have one reach you. And he showed me that, in fact, that wasn't correct. But in principle, if you were only maybe something like a micrometer away from your neighbor, some of your neighbor's electrons could get to you. Okay, so that's all parenthetical. All right, so I don't know how many things I've told you about quantum mechanics that I've told you are strange, but you may find this to be the strangest and totally contradictory to what you've been told about chemistry all along. The angular momentum of an s orbital is 0. And I don't know what happened here in the copy, but this is supposed to be overall angular momentum here. So anyway, it's equal to L times L plus 1 square root of all that times h bar. When L is 0, overall angular momentum is 0. So in case you've forgotten from physics, if you have something going around a center like this, it's got an angular momentum, which is tangential to the circle that you're going around, okay? So if angular momentum is 0, there can't be any tangential motion. All the motion has to be back and forth towards the nucleus. So has anybody ever told you that that's what the 1s electron is doing? It's not twirling around the hydrogen nucleus, it's just going back and forth. It can come back off at different angles, but it's really weird. And this is going to also be true for 2s orbitals, 3s orbitals. All s orbitals have no angular momentum as confirmed by experimental measurements. And so the only motion possible is this. This is not a very eloquent picture, but here's my plus proton in the center. Here's my black dot electron. This is the way the motion is. I don't show it coming back off. It can come off at different angles, but it can still generate a smear of electron density around the nucleus, and all directions are equivalent when you look at it that way. Okay, I have a comment that this is crazy. Yes, it's crazy, but it's true. So you might want to make a list of all the crazy things in quantum mechanics, 0-point energies, stuff like that. You can't, with nodes, how do you get from one side of a problem to the other side of a problem and so on. Okay, next orbital, still no angular dependence. We now have R2 0, N is 2, L is 0. The Y term becomes Y0, 0, and the Y term just winds up adding a normalization constant to it. I've written the function here in terms of rho. Rho is R over A naught. So like that table I gave you earlier for the radial functions, I'm using the rho to make it simpler. Okay, so key point, no angular momentum, still circular. Here's what psi squared would look like. Notice it does hit a node at about 2.5 A naught values. And then there's some probability again further out. I forgot to mention on the 1s orbital that notice at R equal to 0, we have the highest probability for psi squared. And if you worried about that, you might say, wait a minute, how can we stick the electron into the nucleus? That's going to cause all kinds of crazy things. We're not going to have an atom anymore. But as we'll look at later, maybe even today, I'm going to show you that we have to consider the volume that we're looking at. If you're at the nucleus, the volume of a sphere is 4 pi r cubed, and r is 0, so there is no volume to put the electron into. So you have to go away from the nucleus to have any probability. It gets a little bit deeper than that because if you're infinitesimally close to the center and the nucleus is not taking up much space, you're still technically in it, but there's something called a Planck distance that you have to worry about. But for all practical purposes, there is no volume at R0, and so you can't put the electron there. Okay, somebody asked me to explain again about angular momentum in the context of a wave. So that's a little bit of a tricky question, but I'll try to answer it. We used wave mechanics to find the wave function for the 1s or 2s orbital, and we saw it had no angular momentum based on quantum mechanics from the stuff that I gave you in the last section on quantum mechanics. All that stuff with angular momentum about z, and so on. So I didn't go into that very, very deeply. But angular momentum has to be tangential to it. So we're ignoring the fact that it's a wave. That's not an intrinsic part of it. We're just using the formula that we got from wave mechanics to indicate that there could not be any angular momentum for s orbitals. So that was kind of a muddled answer, but I think just look at the equations and accept the fact that L is 0 gives us 0 angular momentum, so there can be no tangential motion for a particle trying to go around a nucleus. Okay, so now here we get to where it's fun, and I think you probably haven't seen this before. Let's take the 2p orbitals, and we'll first take, I'll take n equal to 2, L equal to 1, and first I'm going to take m sub L equal to 1, and then I'm going to take m sub L equal to minus 1. There are 3 possibilities because we have 3 p orbitals, and each of those orbitals is defined by a particular m sub L value. I think, we have talked about degeneracies before. When we talked about the particle in a box, I gave you a little table telling you how many different wave functions could correspond to the same energy. For the, this is true actually for all atoms. All of the p orbitals for hydrogen, even though hydrogen doesn't have electrons in its p orbitals, it still has the p orbitals. All of the p orbitals have exactly the same energy. And this is true for uranium, plutonium, anything else. And so we say they're triply degenerate. We can write distinct and different wave functions that correspond to the different m sub L values. So here is R21. First of all, this will apply to all of the n equal 2 orbitals that we have. It would also apply to the 2 s orbitals, but this is the R function that we have. But this is not what's going to give us the shape of the orbitals. This will give us the energies. All right, well, the angular part looks like this. So we go along, we have our wave function, we have dependence on theta, and lo and behold, we have e to the I phi. So we have an imaginary term. You guys are all familiar with Euler and his expressing it in the real and imaginary parts. But this is kind of an unfriendly thing to look at. And so for reasons that we'll see, we're going to try to get away from this. We don't want to have the imaginary part here. If we write the m sub L minus 1 orbital, it looks just the same, except the plus I has become a minus I. All right, well, it turns out that you can't represent these orbitals because of the imaginary terms very well. So we're going to wind up doing something to them by applying a quantum mechanical rule. So you'll wind up with orbitals that look like what you saw in freshman chemistry. But before I get into that, let me point out that you can have a real function for m sub L0 and looks like this. It doesn't have the imaginary exponential term. Okay, here's a question. Where are the equations for R and Y coming from? These are solutions that Schrodinger figured out for the expression. Okay, so he had a form, when he was doing this, obviously he didn't know the Schrodinger equation to begin with. He had to figure out what was the nature of the equation so it would give it the correct results for the hydrogen atom. And he realized in the process that R and Y could be separated into two parts. So these are exact solutions that are basically coming out of the Schrodinger equation. As I've told you, I'm not going to have you responsible for solving quite a few of these quantum mechanical equations. But again, in this case, if you wish, if you're a masochist, take one of the radial functions, plug it in to the radial part of the Schrodinger equation, and you'll see that it is a solution to that eigenvalue, eigenvector problem, which is a kind of differential equation. Okay, so keep in mind, so all of our functions are given by R21 in this case, and then Y1ML. The 2 means n is now 2, L is equal to 1, and here L is equal to 1, and then we can have M sub L. So the mathematical solution to the angular part of the wave equation are what I've given you above, and these orbitals would be called P1, P0, and P minus 1, and the subscript indicates which M sub L value you're using. A lot of theoretical chemists and most physicists use these orbitals when they look at atoms. They do not talk about Px, Py, and Pz orbitals. But as you can imagine, people who teach freshman chemistry don't want to be talking about imaginary space when they're talking about orbitals. P1, P0, P minus 1 are a perfectly good, in fact, even preferred set of mathematical solutions for which we can represent probabilities for where the electrons are. But P1 and P minus 1 are in imaginary space with the square root of minus 1. So we're not very happy with that. So as I said, chemists, be it freshman chemistry or organic chemists, they typically don't like quantum mechanics and they want things as real solutions. I think I've told you that, if I remember correctly, there are 15 basic postulates of quantum mechanics. Things like solutions to the Schrodinger equation always have to have orthogonal wave functions and so on. One of the postulates we haven't talked about is if you have several solutions of the wave equation for the wave functions, linear combinations of these are also solutions. So that means I can add or subtract them together and come up with solutions. Now you have to be careful when you do that. When you do it, you have to make sure that the final functions remain orthogonal. You have to make sure you can still normalize them. And you have to wind up with a complete set. But this is the basic rule that we're going to have. So notice up here what we have. This is the y for m sub l minus 1. This is the y for m sub l, sorry, here's the one for plus 1, here's the one for minus 1. And they look exactly the same, except for this exponential term. And when you expand the exponential term according to Euler, the top one will have a plus sign for the I sine phi. The bottom one will have a minus I sine phi. So we're going to add these two terms together, and we will come up with an expression that looks like this. Well, sorry, this is where we start from. So this is expanded from the Euler formula for m sub l plus 1. This is expanded for m sub l minus 1. So now I'm going to make the addition, this plus this, and we will get a result looking like that. So we'll have a normalization constant that we will have to modify after we do this addition. And then in front of here, we're going to have this term. We'll have a sine theta and a 2 cosine phi. Notice absolutely no imaginary term in it. And in fact, we're going to define that this wave function is the wave function for the px orbital. Mathematically, it now winds up looking like this. We have a big constant in front, then sine theta cosine phi. If you go back to your relationships between spherical and Cartesian coordinates, you might remember that r is equal to x sine theta cosine phi. I don't state that on the next page, but anyway, the shape of this description will be something pointing in the x direction with a little bit of expansion as that. I'll look at that in just a minute. One of the other rules of quantum mechanics is if we make a linear combination of two orbitals, we have to wind up with two orbitals. So we can't just make the positive combination here, we make the linear combination. And when I was writing these notes, I was very careless and I forgot to put in the sine theta term. So just because it's shrunken here, don't disregard it, it's still part of the function. So this result, subtracting p minus 1 from p1, gives us this expression, sine theta sine phi times a big constant. And mathematically, this is equivalent to y over r. So this is going to wind up being our py orbital. The pz orbital, luckily, we don't have to do anything to it. It's already pointing in the z directions. Some of you have graphing calculators, so you can probably plug in these kind of functions and see what the magnitude of a constant times this is going to be at different theta and phi values. And you will see this will look like p sub y, this will look like p sub z, this will, the top one up here will look like p sub x. But here's the main point I want you to remember here. We made linear combinations, and we generated a new set. The px, py, pz set is a perfectly valid set of three orbitals when we use them all together at the same time. Many of you chemical engineers, I think, take inorganic chemistry. Some of you might want to take it. In my other class, I have to make sure that those that are in the inorganic course, they realize there's nothing wrong with px, py, pz orbitals. They will be using them all the time to better characterize inorganic molecules. But mathematically, the p1, p0, and p minus 1 orbitals are a preferred set because for p1, you know what m sub l is. It's equal to 1. If you take a p0 orbital, then you know it's 0. For p minus 1, m sub l is minus 1. When you go to px, py, pz, these are hybrids. If you're in a px orbital, you've lost totally track of what that angular momentum m sub l is in some specified direction. But whenever you're doing problems or analyzing molecules or in organic chemistry, you would have talked about px, py, pz, that's perfectly fine. But you can't mix and match them, but you can use either this set or you can use that set. All right, well, these are the pictures that you would get. Light areas represent where the wave function squared now, uh, uh, well, these are pictures of the wave function squared, but the light area represents where the wave function is positive. The dark area represents where the wave function is negative. And so we're going to have to be careful that we avoid any confusion in the future when we talk about the sign, SIGN, of the wave function. And that's different from the plus charge that we have on a nucleus or a minus charge that we have on an electron. All right, so you've all seen these before. Px orbital pointing in the x direction, Pz pointing in the z direction, Py pointing in the y direction. This is my sloppy way of drawing it. Just we put in a plus and a minus. Whenever I draw these orbitals in the future, when we talk about molecular structure, then be aware that these will again not refer to charges. The electron is always minus, and so we're going to have minus charges in these individual lobes that we have. Okay, so here's my warning here. The plus or minus is the sign of the wave function. Okay, well, here's a quick picture of the radial curve for the 2p orbital. It is 0 at r. It has a peak, and then it drops off exponentially and finally dies out. I'm going to take 1 minute more before we end class and tell you what we'll talk about in the next lecture. Now, if you tuned in late, and I will send you an email confirming this, we will not have a live class on Friday. I don't think I'll have time to prepare the lecture to be put on eCampus before then, but it will get done by sometime Saturday. And I will also do a second lecture over the weekend, so we're caught up. So you will have 2 lectures, hopefully, that you can look at before we get to Monday's class. I will try to make those lectures short, but anyway, do try to look at them and read your emails, follow your emails for what we're doing. Okay, again, sorry for messing things up Monday, and sorry I also have to be away on Friday. Any questions before we start? Okay, thank you all. Take care. Someone asked, is it normal not to understand? I refer you back to Richard Feynman, the famous quantum mechanicist. Don't trust anyone who tells you they fully understand quantum mechanics. So we know what some results come out of it. They're quite different, like the no angular momentum for a 1s electron, the way it moves, 0-point energies, nodes, lots of weird things. But every time anyone questions anything, it gets proven. So we talked about the Stern-Gerlach experiment and how you had only different orientations of angular momenta that you would have in systems. That's all been tested experimentally. There's a question of why doesn't the electron collide with the nucleus? We'll talk about this next time. The deep explanation for that is indeed very deep. In fact, I'm not sure I understand it. Nuclei are very complicated, but they keep electrons away. You probably heard about the main forces of physics. There's a strong nuclear force, there's a weak nuclear force. We have electrostatic attractions, and people are trying to find some universal explanation that puts all these forces together. But what we'll see next time is basically you have no volume unless you're outside the nucleus, and that's how you can get electron density. So there will be a finite, very, very small probability of the electron getting close to the nucleus, but it can't get into it. Hope that helps. Okay, signing off.